Right. Good morning, everyone. This is Chi Yao from CARB. If you can hear me fine, please give me a thumbs up on the chat box so you can also test out the chat box. Great, I can see some of the thumbs up. So welcome everyone to our real world tire and brickware emission seminar today. And it's 10 o'clock, so we're going to start now. And anyone can join at any time or leave the meeting. The recording will be available later on and uploaded to the CARB website. So I will give a brief introduction before the researcher gave us the seminar. So let's start with some ground rules. So the meeting will be recorded, as I just mentioned, and the final report and presentation slides will be available online after this meeting. Please allow us some time to upload the files, and we encourage all the questions after the presentation, and everyone will be muted during the presentation. Please use the chat box to type in your question or raise your hand, and I will point out the names to, I will read out loud the questions from the chat box. And again, if you have any comments or questions after the seminar, here's my email, qi.yao@arb.ca.gov. You can always email me after the seminar to give us your questions or comments. And so this is the online website that you can find this project. So this is how it looks like, and the final report and the presentation will be uploaded onto this website. So this website is also, the address is also included in the meeting description. So if you don't remember exactly the website address, you can find it on the meeting description on Zoom. All right, and so this is our motivation for this research. So on the pie chart here, it shows a estimation of PM2.5 emitted from the on-road vehicles, and it broke down by different sources. So we can see this is from 2020 data, and we just passed 2020, and brake and tire wear in blue and yellow combined already emit more than exhaust from the on-road vehicles. So that was our biggest motivation to start this research project with UC Riverside. And also our governor started a new executive order that we're not going to sell any new gasoline powered cars and passenger trucks by 2035. And that will make brake wear and tire wear more relevant in the near future, especially in California. So we would like to explore the magnitude, the physical and chemical characters of the brake and tire wear emissions. And I would like to also give a brief introduction of today's speaker and also the PI of this project, Dr. Hae-Jun Young. He's a professor at UC Riverside, also affiliated with CSIRT. So his research interest is in aerosol science and air pollution, and you can find more about his research from this website and on this page. So if we don't have any questions about the introduction, I will start sharing the presentation and give the floor to Dr. Young.
Thank you, Chi, for introduction.
Yes, please request the control.
Oh, I see. I'm sorry. Request remote control.
So, yeah.
Okay. Can you hear me well?
Yes.
Okay. So shall I start?
Yes, please.
Okay. Thank you, everyone, for sparing your time. So let me start by acknowledging my co-presenters. So this will be co-presented by co-PIs. So first, Xiaoliang Wang from DRI, Anthony Chen from University of Nevada, Las Vegas. Kyunyan Wu couldn't be present because he has time conflict, and Max Zhang from Cornell University. I'm sorry. Okay, so this project was funded from CARB in 2018, and there were 4 program managers I would like to thank. So Seung-Ju Yoon, Chi Yao, Chris Roll, and Sonia Collier. And also there are many CARB staff who attended monthly meetings giving inputs. And also I'd like to thank South Coast AQMD staff, especially Renee and Keith and others who allowed the team to access their near-road sites, both in Anaheim and Long Beach, and also business owners and managers who allowed access to their parking lot for open site management. Okay. Okay. So next, there were many people involved in this project. So most of the effort were done by students and staff. Brenda Lopez was the leading graduate students who oversaw all of those activities or measurements. Chas, Steve, and David, Jerry, Ling, and Jesse, and Chango did their part for this difficult field measurements. I also would like to thank contribution from my colleagues. They were all in-kind mostly. Manabu Shiraya at UC Irvine did parallel health effect study, which was published by co-measuring some samples. Ki Hong from Gwangju University Institute of Science and Technology did in-kind contribution of chemical analysis. Stephen Ho did detailed chemical analysis. Markov Prinsvak from UCR contributed to measuring turbulence. And Gunter at CARB provided tire samples. Tyler Beck from Particle Instrument provided LP. Yusuke Mizuno at Horiba provided 4 units of PX375, and TSI provided QCMOD. Not all of the data will be presented during today's talk, but they're in the report. Okay. So this is how the presentation is going to be presented. So first, background and objectives. Second, I'm going to talk about field test in terms of location, instruments, and measurements. And result sections will be presented by each co-PIs, and then final lessons. So this is one of the graphs that nowadays many of us are looking at. So let me take time to explain this. So this curve shows first at the top, the black dotted line shows how vehicle miles traveled are increasing from 2000, 2010 to 2015. And then if you follow this orange line, this is how the tailpipe emission, exhaust emissions are reduced and being reduced and expected to reduce, thanks to the stringent regulations. If you follow a yellow line at the bottom, you can see they are low, starting low in 2000, but they are gradually increasing as vehicle miles traveled are increasing. That's representing brake wear particles, and they are almost crossing over with tailpipe emission in around 2020, which when our measurement was done, and tire wear emissions are following a similar trend. So the objectives of the study were to measure time reserved PM 2.5 and PM 10 mass at near road locations to quantify exposure at near road locations, so that we can understand how communities downwind of these places are affected. Second, to measure real-time particle number distribution and semi-real-time metal content, and to distinguish brake and tire PM from other emission sources, including background and tailpipe emissions. Another objective is to conduct source apportionment so that we can determine contribution of brake and tire particles, which are non-type of emissions, to the total PM 2.5 and PM 10. Our next objective is to determine unique tracers by doing source apportionment for brake and tire wear emissions. And the next thing is to do dispersion modeling to evaluate impact of brake and tire wear particles on nearby communities at downwind location. So we had a lot of things in our bag. So let me first explain where we did testing, what instrument we had, and what kind of measurement we conducted. So this is a Google map of Southern California, South Coast Air Basin. What you see is two locations. So these yellow lines are all major highways. So this is basically a web of highways in Southern California. So we identified, first we actually looked at locations where South Coast AQMD has near road measurement locations so that we can take advantage of existing site development and measurement. Then we identified these two locations are most promising and meeting our need. So first location was at Highway 5. You can see on the right side of the inset, this is a picture of Highway 5. This is near Disneyland on the left side. And then here at the red dot, small red dot shows a near road measurement location, near road monitoring station of South Coast AQMD, where we co-located our instrument and sampling devices. And then across the road, where there is a parking lot of a certain hotel, I cannot disclose the name. And then there in the parking lot, we placed our upwind measurement sampling devices there. On the left-hand side, there's Highway 710, which is known as heavy-duty corridor. And this is stretching from north to south. And heavy-duty traffic is typically 8 to 10%, whereas at Highway 5, it was 4 to 5%. So it's little more than what you see in Highway 5 in Highway 710. It's more than that. And then it's going to, again, north to south. And then here we have a upwind location at this shoulder. There's a very wide shoulder in Highway 710. This is LA riverbed on the right. And this Highway 710 on the left is industrial areas of Compton and Long Beach. I'll give you more detailed picture of where the sampling has occurred. So here, this is again Highway 5 location, Anaheim, and this is where the red arrow ends on the right bottom. Here is where our downwind location, assuming wind is blowing from left to right. So on the left bottom, there's a wind rose during our 1 week sampling period. So wind was mostly southwesterly, so wind blowing from southwest to the northeast. So as such, this is going to naturally downwind, although wind sometimes rotates. And then here is our upwind location. In addition, South Coast AQMD in this location has background location at the upper left, which is called Pampas Lane location, which was measuring CO, NO2, ozone, PM10, PM2.5 continuously, and time integrated samples of PM10 and PM2.5 so that we can compare. In Long Beach side, it's a little bit different. As you can see, a contrasting difference is on our upwind location. There's industrial areas where lots of heavy-duty vehicles are passing by and lots of operations are happening. So there are a lot more sources in the Long Beach location, and down bottom on the left shows wind rose during our sampling period. This was our upwind location on the top middle top here. This is HMD near road measurement stations. And then here at some parking lot of certain private location, there was our upwind location. So it's a little farther here. When wind is blowing, basically south westerly. Yeah, it's the same. But the road is slanted this way. In terms of our measurement, so today we are going to present mostly, time reserved gravimetric sampling. So this is DLI's medium volume sampler, which pulls samples for both Teflon and quartz filter medium. And our sample period was divided by 4-hour block from 6 in the morning to 10 in the morning, 10 in the morning to 2 in the afternoon, 2 in the afternoon to 6 in the evening, so that we can capture morning rush hour and early congestion in the evening, and then afternoon traffic, and late morning and early afternoon traffic. And first week so the first measurement was done at Highway 5, totaling 18 sets of filter samples. And another week was conducted at Highway 710 in 2020, collecting 14 filter samples. In terms of chemical analysis, we had gravimetric PM mass quantification and X-ray fluorescence for metals, because breaks are typically metals in terms of chemical composition. We also conducted ECOC analysis for tape-out emissions, ion chromatography for ions, and thermal disruption GCMS to measure markers for tires, and pyrolysis GCMS to measure rubber markers, styrene, isoprene, and others, and also ultra performance liquid chromatography for some markers of tire wear. Okay, so let me hand over the research section, chemical composition, to Dr. Xiaoliang Wang. Xiaoliang, you have to request a remote control.
Yeah, I did. Good morning, everyone. My name is Xiaoliang Wang at Desert Research Institute in Reno, Nevada. So my responsibility was to collect filters and conduct chemical analysis. Trying to advance. Okay. So this slide shows the mass concentration of PM 2.5 and the PM 10 measured at Highway I-5 and Highway 710. The solid lines shown are the nominal downwind sites, and the dashed line are showing the nominal upwind sites. The group of the two lines on the upper side are the PM10 concentration, and the lower one the PM 2.5 concentration. So you see there's some diagonal variation of the concentrations. Typically, highest concentration occur in the morning rush hour from 6 to 10 sampling period. Especially, it's very clear in the Highway 710 sampling site. It's mainly driven by the low wind speed and low dispersion during this period. So overall, the PM 2.5 concentration was about 10 to 15 microgram per cubic meter at these near low sites. And PM10 concentration was 2 to 3 times higher, around 13 microgram per cubic meter. And the difference between the upwind and downwind sites are about 1 to 4 microgram per cubic meter, which is not that great and not that big. And this slide shows the mass reconstruction of the particulates into major PM composition categories. Here, I assume the organic matter, OM, equal to 1.2 times organic carbon. This is because the dominance of the fresh tailpipe emission. Then for mineral dust, we use the improved formula to assume to calculate the dust concentration from these key elements. And these pie charts show that for PM2.5 on the left-hand side, the organic matter is the dominant particle composition, ranging from 33 to 37%, followed by mineral dust, about 30%, and elemental carbon, which is a known tailpipe emission marker, is around 10 to 15%. For PM10 on the right-hand side figures, the mineral dust are more abundant, ranging from 42 to 45%, followed by organic carbon, organic matter. And one thing that interesting is the nitrate has more abundance in PM10. This is because nitric acid will react with sea salt and the mineral dust to present in the cost side reaction. And this slide shows the comparison of these major chemical composition at the upwind, downwind sites, as well as at the two highway sites. So if you look at the two bars comparing upwind and downwind, the downwind concentration are higher than the upwind site, although there are a lot of sample to sample variation, so the statistical significance is not great. What is significant is the elemental composition at Highway 710 is about 20% higher than those at Highway I-5 because more heavy-duty vehicles on 710. Sulfate is similar because this is usually a secondary pollutant and regional. And you can see the ammonia and the nitrate are much higher at 710 than I5. These are mainly due to two very high concentration event of ammonium and nitrate in 2 foggy days. These two tables compare the elemental composition at the two highways. So we focus on a list of elements that are abundant in low dust as well as in vehicle or brake wear. And the green fonts highlights the high correlations as expected. Silica, calcium, aluminum, and potassium, these are known to be low dust main compositions are crustal materials. So these are highly correlated. We also found that the elements enriched in brackware, such as barium, copper, and zirconia, are also correlated. So elements from common sources I usually have higher correlations. So this can be used for source apportionment to find markers. And this slide compare the distribution and the concentration of PAHs at the two highways. The first impression is that they have similar distributions at the two highways. The difference is that Highway 710 have higher concentration of these two lower molecular weight PAHs, which are known to be abundant from diesel emissions. And overall, the PAH concentration at excuse me, Highway 710 is 47% higher than those at I-5. This slide compare the two type of tire particles. So thanks to Dr. Gunther Engelen and Oliver Chan from CARB that provided these tire particles sampled from the CARB MOD lab. So these are not size separated. So these are total TSP, total suspended particulates. And we analyze the chemical composition of these two types of tires. And you can notice there's significant difference between silica. Silica is used as a filler for tires. And also difference the elemental carbon. There are 10% difference. The butadiene rubber and the styrene butadiene rubber are almost the same for these two type of tires, but the natural rubber is much more abundant in the Cooper tire. So these are only two type of tires because different tire manufacturers, they use different formulas for different applications. Some European group, they are collecting hundreds of tires to analyze the chemical composition, which is important for source profiles to separate the tire contribution from other sources. So as a summary for the chemical composition part, we measure the concentration of PM 2.5 and PM 10 to be 10 to 15 for PM 2.5 and 30 microgram per cubic meter for PM 10. The organic matter, mineral dust, and the elemental carbon are major PM compositions. The concentration of elemental carbon and the particulate PAH were higher at 710, likely due to their higher heavy-duty vehicles on the highway. The high correlations are found for elements with common sources, such as brickware and road dust. The rubber abundance are different in different tires, which call for more analysis of different tires. Next, I will turn my to Anthony for source apportionment.
I think I have a request. Okay. Okay, I can control it. Hey, good morning, everyone. My name is Anthony Chen from University of Nevada, Las Vegas. I'm going to talk about the source apportionment part of the study. And thanks for the chemical speciation data provided by my colleagues. So as you know, our upwind and downwind side are so close to each other. So they are impacted by the same level of urban background. Therefore, the upwind and downwind difference may be entirely attributed to the on-road traffic emissions, which of course including the exhaust and the non-exhaust particles. So here in this bar chart, we shows the downwind, average downwind chemical composition and I5 subtracted those from the upwind measurements. So this is the starting point of our CMB, the chemical mass balance source apportionment. We use this sample to do our sensitivity test. So I would like to briefly go over the chemical mass balance formulation. So as you can see the formula here, it assumes that the ambient observation in this case is near row measurements are linearly related to source profiles and the source contribution. So if we provide the source profiles to the model, we will be able to determine the source contribution based on the effective variance regression method. So, and this calculation can be carried out either by EPA Cmb 8.2 model or by the hybrid environmental receptor model. In this study, we used hybrid environmental receptor model that basically will give you the same results. So in the CMB analysis, the most important thing is the source profiles, right? So here I show you some examples of the source profiles explored in this study. We have the break source profiles coming out dynamometer studies back in 2004 and 2020. And the tire profile is actually developed in this study from the tire dust collected in the lab, and they are analyzed by the same chemical composition as those in ambient samples. We also collect the dust at both monitoring site to develop the local dust profiles. And then for exhaust profiles, it also come from the diameter studies back to 2001. Although these profiles are kind of slightly old, but they do contain all the organic markers we like to include it in this study. And when we compare the other chemical components such as organic carbon and elemental carbon, we find them compare pretty well with the more modern exhaust source profiles. And here I show you the bar chart shows the source profiles. Most important markers for this source profile also indicate. For example, for this brake profile here, titanium, iron, copper, and the bearing are forgot to mark bearing here, but they are important markers for the brake wear. For tire wear, zinc and organic matter can be important markers, while silicon, calcium, and maybe iron can be markers for the road dust. And then for exhaust profiles, the most important marker will be the PAHs and Hopian and sterins. So here is the sensitivity test, the results of our Cmb analysis. The most important thing for the sensitivity test is to identify the best combination of profiles that can explain our ambient observations. In this case is the upwind and downwind difference. So after several trials, that we are able to identify a 6-source combination which can best explain our observations. And these 6 sources include 1 dust profiles, road dust profiles, and the 2 brake profiles, one with high copper content, and the other one with the low copper content. Okay, and then 1 tire profiles, and 1 gasoline diesel exhaust profile. So this 6-source combination resulted in the highest R-square and the lowest chi-square, which suggests that they can best explain our observations. So now, here is the results of Cmb Mp Metrics. This Mp Metrics indicate the most influential species for each source type, which offer an alternative way to determine our model performance. So as you can see here, the most influential species identified by Cmb agree pretty well with known source markers. For example, for the first brake profile, the most influential species is iron and barium, and the second would be titanium and copper. So these 4 compounds are known markers for brake profiles. And the zinc, organic carbon do show up for tire profiles. And then we know the aluminum, silicon, calcium, not surprisingly, they all show up for dust profile, which are now markers for the geological material. So basically, we see this Mp metrics support our Cmb conceptual model. So now that we identify the best combination of source profile for Cmb analysis, we applied to all the upwind and downwind samples. And here I show you the results of a PM2.5 source approachment at the downwind site at I-5 and Highway 70. So you can see a lot of sample to sample variability throughout the campaign. But overall, the sources can explain the PM2.5 concentration pretty well, except a few outliers that we see at Highway 70, likely due to some unknown sources not included in the model. So you look at overall average, we see that the road dust are pretty dominant, account for 33% of the PM2.5 mass at I-5 and 24% at the highway 70. And the brake account for 18% at the I-5 and 8% at highway 70. And tire is 12% and 7% at both sides. And if you look at the exhaust fraction, which is you combine the gasoline and diesel emissions, explain about 19% at I-5 and 20% at highway 70. So you can see here, even for PM 2.5, we see contribution non-exhaust particles already rival those of the exhaust particles. Here is the results for PM10. Again, our model can explain the PM10 mass pretty well, except a few outliers at the Long Beach here. And basically, we see that even more dominant contribution from non-exhaust particles. In this case, PM10, road dust account for 53% of PM10 at the I-5 and 32% at highway 70. And then, I mean, the exhaust only exhaust particles, gasoline and diesel combined only spread 6% at I-5 and about 8% at highway 70. We do see more diesel fraction at highway 70 than I-5, which agree with our traffic mix. We do see a lot of unknown kind of others, which is the mass is not identified by Cmb analysis. Partly can be attributed to sea salt because it's not included in our model. So this slide is showing the upwind and downwind difference at both I-5 and highway 70. Basically, we see the label exhaust particles, diesel and gasoline, are similar between the downwind and upwind samples, while we do see a higher level of non-exhaust particle at downwind side. So we think that because the on-road traffic emission can impact both downwind and upwind side through the vacuum and the turbulence missing transport. And turbulent missing is probably more important for fine particles. And most exhaust particles are fine particles, so they can impact the downwind and upwind side more equally compared to these non-exhaust particles. So, and this is substantial others, we observed the highway 70 close to Long Beach. It may be attributed to the fresh aged sea salt because the site is closer to the port. We do see higher chlorine and sodium concentration in some of the samples collected at this site. So here is a summary of our source approachment results. So if we average over the upwind downwind samples, we found that the non-exhaust fraction, brake and tire combined, their contribution exceeded those exhaust fractions for I-5. And the two are more comparable at highway 70. And for PM10, the non-exhaust particle contribution are 2 to 3 times of the exhaust contribution. And we just look at the compare the brake wear and tire wear particles, we see that the brake wear generally contribute more than the tire wear particles at both sides. Although the CMB results based on the our uncertainty assessment, the contribution for tire wear has higher uncertainty because we have more variability in the source profile. So we do still need a more representative the tire wear profiles to refine our findings. Okay, that's all I have today. I'm now going to give the stage to Max. Thanks.
Max, you need to unmute.
Okay, can you hear me now?
Yeah.
Hi. Some kind of technical difficulty here. All right, so I'll quickly present our modeling results, right? So the main objective for this part of the project is to get some understanding of the impact of or exposure impact of those exhaust and non-exhaust emissions, right? On the downwind communities, and you know, there are challenges. The main challenges is that in order to do a good job in terms of the modeling or exposure assessment, you sort of need a good input, right? You need to know the emission profiles of those exhaust and non-exhaust particles, and also you need a boundary condition like what's wind speed, typically at function height coming to the domain, right? So, and typically, and often the case here is that you typically don't have a very extensive measurement enable us to quantify all of those, right? So, you know, that's why, you know, people said nobody believed the modeler, right? So it's not the modelers themselves, right? So, and so our strategy here is that we will try to make best use of the field measurements as much as we can, right, to constrain the model, right? So to reduce those uncertainties. So that's why, you know, then to make it much more realistic, right? So so in order to do that, we implement so-called two-domain approach to do that. So you know, this is, if you can see my cursor, this is the larger domain here, and we have one domain. So there are two domains. One is what we call the highway domain, is right here, right? The other is a community domain, and as you can see here is the Anaheim site, the near road site is both domain, right? So so for the highway domain, so the idea is we will use Anaheim, the near road site anemometer measurement at two different heights, right, to constrain the inlet velocity profile for the community domain. And then we use the concentrations or site distribution measured at this site as the boundary conditions, right? So you can imagine for those narrow community domain, right? So you have a invisible vertical surface, right? So you know, from this narrow site, right? And then you had a wind coming in, also had the particle concentration specified at the surface and being blown into this community here, right? So that's the general idea of the two-domain approach. So also for the community domain, as you can imagine, as you can see here, is quite complex, right? So with a lot of buildings, very crowded. So in the modeling, we had to simplify a little bit, right? So still retain the characteristics, but not a one-to-one representation of the domain. Also, we try to identify the conditions where more represent a steady state, so that can further reduce the modeling uncertainties. So based on this, I think Xiaoliang showed something like this before. We identify the period with almost perpendicular wind and particle measurement is very close, not exactly the same time, but very close, right? So this we are more like treated like a quasi steady state. So this is essentially this period is our modeling period. So this is the input to the modeling. We had the inlet profile. Like I said, we need the velocity as function of height, right? And also have a inlet, as this is as the imaginary surface, right? Had the particle concentration measured at the neural site, and we also simulate the vertical profile, right? So now, now you can extrapolate to the entire heights of the surface, not just at the near the ground level where the measurement was taken, right? So, in quick summary of so far here is all we spent quite a amount of efforts try to utilize the field measurement data as much as possible as input to the model, right? And try to reduce modeling uncertainty. Just quick summary of snapshot of what we can see here is one question is that the key question for this investigation, part of the investigation is what is the role of deposition, right? So as we know, non-exhaust particles tend to be larger than exhaust particles, and then you imagine the deposition pretty much bigger roles, right? So we look at the 4.5 micron. It's more or less representative of brick PM, and 10 micron representative road dust. And we found that for the brick PM deposition, probably somewhere 1 to 2% reduction, right? By deposition, and for road dust, a little bit higher, right? But at the same time, you still see relatively high concentration, even though there's a reasonable significant contribution from deposition. And just another recap here is we use the two-domain approach to try to reduce the model uncertainties. We look at impact of depositions, right? So it's there, but it's still does not change the fact that the non-pure particle still has a significant impact on the neural community as compared to the pure emission. All right, thanks. Xijun, what should I do?
I'll be taking over. Yeah.
Right, thanks.
Thank you. Next. So lastly, I want to share one of the interesting results from particle size distribution measurements. The next slide. So aerodynamic particle sizing method has been used to measure particles larger than 1 micrometer because SMPS typically used a size classifier is based on mobility measurement. It doesn't cover super micrometer particle size just because the column itself becomes too big. And so most of researchers has been using aerodynamic based sizing instruments such as TSI APS or Decouple LP. So the slide, the picture on the right top corner of this slide shows a study conducted in the laboratory. So Link Engineering and ERG conducted brake dynamometer testing for a variety of light-duty vehicles at a non-deceleration rate. And these are size distributions in terms of aerodynamic diameter they have measured. And as you can tell, it shows a peak at 2 micrometers. Oh, by the way, there are also particles below 1 micrometer and also volatiles, but that's not of our interest at this point. So you can remember that this is what lab has measured. And remember, on the road, near the road, there are lots of other sources. So you are not hopeful to see this happening and showing up in the size distribution, but I think we found something interesting. The graph at the bottom shows 1 hour averaged LP measured aerodynamic particle size distribution. So this axis here is time chart. So this is at the Long Beach location, but Anaheim location actually shows the same thing. So on the left, it shows overlaps of tailpipe emissions. That's why the peak is appear to be broad because they are overlapped. And then there are 2 peaks here. And we looked at these peaks carefully just to make sure these are not artifacts of the instrument and are way above detection limit. And it turned out they are real Earth signals. And interestingly, the peak in the middle, actually this arrow is mispointing. So this should point this peak in the middle at 2 micrometer is coinciding with a peak which was measured at in the laboratory. So we believe that brake particles can be detected at the near road if you do the real-time particle size distribution measurement. And we believe, we believe that the next peak, which is at the larger size, like about 10 micrometer or 7 micrometer, is probably dust or maybe some tire particles are included, but that was not actually too obvious for us and didn't have enough time to look into that. But we believe that 2 micropeak in number distribution is the brake mode diameter. And what when Max said 5 micrometer, he meant in terms of mass mean diameter. Okay, with that, I'd like to conclude the presentation. So just to recap that in our measurement at near road 2 near road locations, and PM 2.5, PM 10 were 10 to the 15 or 30 microgram cubic meter respectively. And at 2 locations at Highway 5, non-tailpipe emissions were higher than tailpipe emission, 29 to 30% versus 19 to 21%. So 29 to 30% is contribution of non-tailpipe emissions such as brake and tire at Highway 5 versus 19 to 21 is a contribution of the individual particles. Whereas at Highway 710, they were comparable, although the absolute mass concentration was higher at Highway 710 locations. And for PM10, Xiaoliang already has mentioned that it was 2 or 3 times higher than PM 2.5. Oh, sorry. And then particle size distribution, as I mentioned, shows some signature of brake mode in the real road near road measurements. And the last is what Max has said, that deposition of 5 micrometer of brake particles is 1 to 2% to the downwind communities, whereas that of supposedly tire size range or dust size range is 4 to 7%. Okay, thank you.
All right, thank you, everyone, Max, Anthony, and Xiaoliang. So now it's the end of the presentation, and I want to emphasize that all the recording, report, and the presentation will be available on CARB website in June. So I'm actually going to be on vacation next week, so it'll be after next week. Also, I'm going to read out loud the questions in the chat box for the recording purposes. And after that, everyone feel free to raise your hand or put more questions on the chat box. So I will start with the first question from Mark. That sounds more like a statement, but I will still read out loud. Tire is probably proportional to vehicle weight, which is true. So RMI's work on 800-pound crossover SUVs is germane. This sounds more like a statement to me. So unless Mark, you want to elaborate that, I will pass to the next question. Feel free to unmute yourself, Mark. All right. So the next question is also from Mark. Have you compared brickware emissions between ICE vehicles and BEVs with low generation and aggressive regeneration? Angel?
Yeah, so I guess I just answered from general perspective because we haven't conducted by ourselves, but we know that CARB conducted some and European colleagues has conducted some. The short answer is that, brake and tire wear, of course, is dependent on vehicle weight and also deceleration rate. And daily driving such as FTP, federal test protocol like or LAC driving like driving, actually, region braking quite alleviate the emissions of brake and tire, and that's actually a hope of agency, I believe. But you're very correct that for USO 6 Act driving, it is anymore. The brake and tire will have more emissions because it's heavier. The vehicle is heavier, yeah, and the friction brake.
Right. Right. So our next question is from Roger. So the 710 site is very near an exit ramp. I would expect much higher brake and tire emission due to deceleration and exit ramp.
Yeah, I was just looking at the map, and it's correct that it's close to the exit ramp, and we actually couldn't find that relationship. But I guess that's something that we have to pay more attention when we do further analysis.
Okay. So the next question is, does PM 2.5 include all particles smaller than 2.5 micrometer, or do you have some cutoff point below which you ignore smaller particles?
So everything below 2.5 micrometer in aerodynamic timing, yes.
Okay. That high correlation of elements in road dust and brickware suggests it is hard to separate the two from sampling.
I guess let me see if I understood the question correctly. So the idea of determining pure correlation, which is how one element is correlating to another, is to find out what elements are related. In other words, we found barium and copper are related because they are both coming from brickwares, right? So the point is, by looking at those related markers, our goal is to separate the contribution of brake PM from all other sources.
So this question is from Yandu, and if you can just answer, if you want to elaborate your question, please unmute yourself. Okay, I guess that answer was sufficient. And the next question is from Richard. Can you clarify the distances from road to each of the upwind and downwind side at I-5 and I-710? Did you evaluate whether upwind rendering of traffic emission could be impacting the upwind side due to vehicle-introduced turbulence created by the traffic on the road?
Thank you, Richard, and thanks for your question. And that's exactly what I am doing right now with my students, to look into the influence of vehicle-induced turbulence. So, the subtracting background PM emissions is not trivial in the near road measurement, especially in the urban location. So, I've been thinking, what would I do if I would do it again? And if I had a chance to doing it again, new from the clean plate, what would I do? Because, there were studies, Decouple did a study both in urban and rural area in Switzerland in 2009 or 12. And then Greg Evans' group did a great study in, I guess it's Toronto, in very big major highway, probably similar to ours, but I don't know how complicated Toronto area is. But the thing is, if we choose rural area, then it's very simple to subtract background because chemical compositions different sources are identifiable. However, The traffic is not going to be as interesting because it's going to be just well flowing. I'm sorry, I guess I have a long answer to your short question. On the other hand, if we choose urban area like we had to choose because we are interested in how much brake and tire wear emission is contributing to the total PM 2.5 in the urban area where most of the population exists, then the difficulty comes how do we subtract background. So getting back to your question, so our Anaheim location measurement location was very close to the road, and it was probably within 10 meters, both upwind and downwind. And of course, in that cases, your description of meandering flow or vehicle-induced turbulence will significantly affect to the transport of PMS from the roadways. So we are looking into that. I would appreciate if you can talk offline for that. And for our Long Beach location, it was a little further than that because of the constraints, because the way the road is built. So we are probably 20 to 30 meters away from both of upwind and downwind locations.
All right, thank you for the answer. So again, if you have additional questions or comments, you can always email me and Hangel. So our next question is from Frank. Slide 24, what does it mean tire dust collected in the lab? Which device was used to create a tire wear? Let me pull out the 24. Yeah, so it was from chassis dynamometer testing lab at CARB laboratory. So what happens is, chassis dynamometer is basically steel or stainless steel, very shiny roller rotating with some rotational inertia while there's a truck or the wheel or tires are rotating. So to prevent a slip of the tire onto that shiny slippery roller, there is actually hashed. The surface of the heavy duty dynamometer of the roller is hashed just to prevent a slip of the tire onto the rolling roller. Because of that, tire wear is happening, and then we put, not me, Gunter put a sampling system there, sucking up suspended tire dust. So it's not going to be the same as tire wear PM on the road because surface condition is different, but at least we could find the chemical composition by doing chemical analysis of those tire dust. Our next question is from Jennifer. Are the light duty vehicle and heavy duty vehicle proportions at the I-5 and I-710 locations representative of other locations in California?
Let me see if I can answer that properly. I am not aware of I haven't looked at the other. So we looked at actually 4 different locations in high traffic patterns in Highway 5, Highway 60, probably Highway 10, Highway 710. So I would say in terms of traffic of Southern California, South Coast Air based on highway traffic proportion between light duty and heavy duty, Highway 5 is close to more representative, but Highway 710 is more pronounced in terms of heavy duty traffic. Yeah.
Right. So the next question is from Mark. Where do the sulfates and nitrates come from?
And Xiaoliang, can you answer this question?
Yeah, sulfate nitrate are typical secondary inorganic aerosols formed from precursors of traffic emissions such as NOx and also from SO2 from other sources.
All right, thank you, Xiaoliang. The next question is from Sonia. For the source apportionment results broke up over time, is there any correlation with traffic level? For instance, more braking leads to higher brake PM fraction, wind, etc.
Yeah, thank you, Sonia, and thank you for the question. So actually, you have an opportunity to read our manuscript sooner or later because Xiaoyang has been preparing that. And in that manuscript, we are describing the traffic is not as significantly changing as we hoped, because we designed the test time, time block of each measurement so that we can capture morning rush hour, late morning and early afternoon, relatively well-flowing condition and a little bit of congestion toward the end of the day around 6 o'clock. That's our intention. However, when we looked at the traffic data, they were more or less similar. But that doesn't mean it's not changing at all because it's changing actually. So my afterthought about this testing is, our current initial analysis so far has been relying on average speed of the traffic. We had some effort, thanks to your contribution and your colleagues' contribution, that we did some license plate reading, image analysis, and so on and so forth. But again, I kept thinking about what would I do if I have a chance to do it again? Then the answer is, based on our intuition and knowledge from lab testing, we already know that heavy duty will emit more, light duty will emit less. It's depending on the vehicle speed and driving and so on and so forth. And that's why some new project, which will be funded from ATI or CARB or somewhere else, will be focusing on on-road measurements so that we can prove that that real-world on-road driving based on individual vehicle emission measurement perspective. However, if we do the measurement at real world, other complication comes in, meaning we don't know how individual vehicles are braking. So again, if someone in this audience has to do this again in a clean plate, think about doing dynamic traffic measurements so that you can quantify different fleet, basically light duty, heavy duty, how they are decelerating instead of just using an average speed. So in other words, some of the results can be better understood if we know how each fleet, light duty and heavy duty, are decelerating in terms of kinetic energy loss, and then relating that to the PM mass we have measured and source of portion. Unfortunately, our analysis didn't reach that far yet, and hope that we can find some and then others can find more.
Thank you for the answer. So our next question is, actually, I can combine the next two questions that from Bud and Ray down. Brake wear particle greater than tire wear particle, I seem to be intuitive to Bud, and also for Ray that he changed tire much more often than changing brake pads, and that higher tire wear emission would be expected to be higher, but how come the brake wear particle emissions greater than the tire wear?
Let me answer that.
Yeah.
So in terms of size of the particles, so brake particles, so Europeans has focused on both, meaning semi-volatiles, which we didn't pay attention much in our measurement because in near world, it's very difficult to capture that resins and adhesives volatilizing in Southern California because we have a lot higher background contribution of semi-volatiles, although our measurement was intentionally done in the wintertime to avoid contribution of semi-volatiles or SOA. In terms of size of metallic particles, you can think of brake particles, you can think of it's like about 0.5 micrometer or 0.8 micrometer, and then the peak is around 2 micrometer in terms of number peak, and then you can always find something larger than that in the tail of the side distribution. For tire, it's completely different story because it's much bigger. It's beyond PM10. You even have PM or PM30, if you can name it, but then it's larger, right? In terms of which one you change more often, brake pad versus tire. The goal of this project is to quantify, the fleet average emissions. But our colleagues, let's say Link Engineering and others, has been testing different brake pad, different tires. There's a wide variety of range of emissions, a factor of 2, factor of 3, factor of 10 difference. So it's difficult to generalize it, but overall, good news is, OEM tires and brake pad seems to emitting less. Aftermarket tires and brake pad tend to emit more.
Right. So the next question is from Shirley. Did we take into account the COVID time when the traffic is unusually lower than normal time?
Oh, yeah. Thanks for the question. So actually, we were fortunate in a way that our measurement and traffic was not affected by COVID. So it was before lockdown. It was before anything. So we were not wearing masks except for COVID. We were wearing masks because we were measuring near the road. So yeah, we were not affected. We were before the lockdown period. Yes.
Okay, so the next question is from Nadine. What are exactly the elements that you use to identify tire wear?
Anthony, can you answer this question, please?
I think the most important element would be zinc. That actually show up in the tire wear profile that Xiaoliang present. And also it's from other literature as well. So there's some organic markers as well, like rubber derivatives and phthalates. But we found that from our Mp metrics, zinc is probably the most influential at this point.
Thank you, Xiaoliang. Our next question is from Roland. How is it the upwind and downwind particle concentrations are so similar? Are particles coming over from other sources? Do wind directions change?
Can you repeat the question again?
Sorry. So it's 3 questions in one part. How is the upwind and downwind particle concentrations are so similar? Let's start with that one.
Yeah. So the contribution of the background particle in terms of mass and size distribution is significant. I mean, especially in terms of mass, is significant. Let's say Sharon mentioned that for PM 2.5 we measured about 10 micrometer or 15 micrometer at the near road location. In that 10 or 15 micrometer sample per cubic meter, the contribution of traffic is about 1 micrometer. And so both upwind and downwind will have the same or similar background contribution. The assumption is the same background contribution. As such, a signal to noise ratio, because we figure the background is as a noise so that we can subtract, is significant.
Right. So the second question from Roland was, are particles coming over from other sources? Do wind direction change?
I'm not sure what that means. I mean,
let me answer that.
Yeah, go ahead.
So yes, the particle come from other sources as well as Anthony's source apportionment. That's what we're trying to identify, different sources other than tailpipe and non-tailpipe emissions. And the wind does switch from onshore and offshore. The switch occur around 10 o'clock to noon time. And in terms of the first question about upwind and downwind differences, so EPA have many near load sites. They have been evaluating the concentration of these near load sites compared to urban background sites. The typical finding of the increment on the near load concentration is 6 to 10% of PM 2.5 concentration. So these are across the United States, over 30 sites.
Right. Thank you, Xiaoliang. I think the additional question was, do wind directions change? And I believe it did through the experimental time.
Yes, that's right.
Right. Okay. So our next question is, can you provide your definition of road dust?
Yeah. So the road dust in my mass reconstruction is it follow the improve the visibility monitoring network has a formula that assume certain type of metal oxides from elements, so converting from the metal the element composition to the load, they actually call it geological material. So it's average over the improved sites which are in the clean environments, which is probably a better estimate of soil particle as compared to road dust. But for this mass construction purpose, we use their formula in our study.
Let me add that in our source approachment, the road dust actually are actual dust samples collected at the monitoring site. So both upwind and downwind. So they are actual. I think it's the surface dust, right? We collected. So it can have deposition from the previous tailpipe, non-tailpipe emission as well. But that's what we use in the source approachment. But the dust contribution are pretty close to those reconstructed dust from Xiaoliang's method.
Right. Thank you, Xiaoliang and Anthony. So hope that answers your question, Kelly. Our next question is on Roger. Should California start testing tires instead of or in addition to gasoline as we gradually switch to electronic vehicles? Which is a really good question that we can really answer through this presentation. But yeah, this is out beyond the scope of this research. Our next question is from Yongzheng. Can you please share levels of uncertainties from your measurements and findings?
I don't know whether we have a slide, but can you, Xiaoliang or Anthony, can you answer what was the measurement uncertainty versus source approachment uncertainties?
In terms of uncertain source approachment, that is come out from the chemical mass balance model in terms of the model fit, how well the model fit the observations, which we already reported in our final report. You can find the number there. Basically, they are large or moderate to large uncertainty to the sample-to-sample breakdown. That's one thing that you see in the bar chart, but each of the contribution also have its own uncertainty associated with that. So which can be pretty large. Overall average, the uncertainty are smaller. But in our report, we do present all this uncertainty for individual and average samples, average source approachment.
Okay. Thank you for the answer. So I'm going to finish all the questions on the chat box, and I will go to you, Eric. So the next question is from Michael. Has anybody looked at the effects of vehicle weight and tire size directly as influences on tire wear particle? Those are the variable of interest as vehicle weight increase and tire size increases.
That's a lab study that's being done and being discussed in other places, but not from this project.
Right. So this is beyond the scope of this project, but we do have studies on that. The next question is, how did you decouple sulfate and nitrate from exhaust emissions? Also, can you comment about what is meant by others? Where are they coming from?
Xiaoliang, can you answer this?
Yeah, that's Anthony question.
Anthony, yeah.
Well, that's a good question. So in our sensitivity test, we don't include the secondary sulfate and nitrate because we think that by subtract the upwind, downwind, pretty much you remove the urban background. Most of the sulfate nitrate come from the urban background because they are secondary species. However, in our source apportionment, we put them back. It just sulfate nitrate, secondary sulfate nitrate profile in the model that contain just nitrate, ammonia, or sulfate ammonia without anything else. So it's an artificial source profile we put in the model to explain the sulfate and nitrate that cannot be explained by other source profiles. So yes, the answer is yes, we do separate the sulfate nitrate from the known sources and also the sulfate nitrate from the secondary process. In terms of others, that can be profile that not included in the model, such as sea salt. We do see high chlorine and sodium, and biomass burning. There could be other industrial emissions. You can look at some of the literature about source apportionment that mainly ambient source apportionment, not really the near road source apportionment that being conducted in California, especially Los Angeles areas. We know the contribution, there are contributions from the biomass burning industrial sources, but generally they are small at this site. So that can be part of others. Basically, the others are the mass that cannot be really explained by the source profile that we included in the model.
Right. Thank you, Anthony. Our next question is from Daisy. What is the percentage of microplastics from tire and brickware? What size are those particles? I think this is not studied in this research project. So, Hinju, do you have any comments? If not, I'm going to skip to the next one.
No, I don't have a comment, but I just saw that from some other article that tires are contributing like a 20% of microplastic, but again, it's beyond the scope of this study. Yeah.
Right. So the next question is from Philip. Will the manuscript provide additional information on particle speciation and deposition such that additional analysis can be conducted on potential health risks posed from exposure to tire brickware emissions?
We actually covered pretty much all of the important results, but some more detailed description will be there, additional analysis will be there. But I guess I can say that our effort of providing journal publication is undergoing, and we certainly will do as much as we can do before it is completely published, because we have a wealth of data.
Right, and also all the manuscript and data will be public on CARB website in June. So our next question is, how are field measured grams per mile compared to unfact values?
Oh, wow.
Yeah.
So that's okay. Thank you for the question. Actually, that's something that the team has been struggling and a lot. So because the idea was, once we do the near road measurement, both at upwind and downwind, the original idea was we subtract the background contribution so that we can come up with the contribution from the road. And then we determine a dilution factor, which is going to be based on either, probably it's going to be either CO2 or CO or NOx concentration. And then compare that with traffic, fleet contribution, and then traffic count, so that we can come up with emission factor. So that was the idea, but the reality was quite different. First, we didn't find good comparison between. We are not sure whether the dilution ratio, because that's again from previous studies. So there are, I would say, there are some studies, but what we kind of referenced was two studies. One is Greg Evans' group's study at the University of Toronto, where they looked at, they actually had a 24/7 measurement of PM mass and followed the background based on urban background, which is very far from the measurement location. And so they came up with PM mass that way. And they pointed out the difficulty is that sometimes it can be asynchronous between what is happening in the background side versus what is happening in the measurement side. But based on their publication, they actually did pretty good separation of the background. We couldn't do that because we didn't have 24/7 measurement data. The other approach was by Nick Bukoviecki's study in 2009 or 12 in Switzerland. What they did was, again, it's 24/7 measurement, which we couldn't afford, but then they looked at markers such as barium 24/7, and they found out when there's no traffic in midnight, there's a background. So we have, to begin with, some difficulty of missing out on important time period where when we can get some good background concentrations. So that can be some sort of excuse. And other thing that on thinking point is that, is it right that our dilution factor we estimate at the near road, if we expect that tailpipe emissions and non-tailpipe emissions will have the same dilution factor at the measurement location? We were not really convinced whether that makes sense or not. So we've been struggling with that analysis. We haven't given up, but it has been very difficult. So if you have any input and if you want to collaborate, I welcome your input.
Thank you for that answer. It was a really difficult question. So our next question is, as the proportion of EVs in California increase, will this result about bakery still be relevant? Oh,
yes. So I guess electrification is a good thing so that we can get away from emissions from internal combustion engine. But what is going against is weight of the vehicle, right? So in the world of auto industry, downsizing and lightweighting has been almost like a religion to improve fuel economy and to improve overall vehicle efficiency. Battery electric vehicle goes completely against in that philosophy because energy density of lithium-ion battery is not as good as hydrocarbon liquid fuel. Well, I mean, so it's good and bad. It's good because you get rid of tailpipe emissions, but it will be really, really interesting to study how the region braking is alleviating, reducing potentially more brake emission from heavier vehicles because there are believers and non-believers. Believers are if you implement certain rules or certain because if you're driving electric vehicles, you can choose the extent of region braking. So if you choose higher region braking, when you decelerate, it actually absorbs most of the kinetic energy, but then your driving comfortability becomes very jerky and actually you might have accidents. So I mean, so then I guess if we or industry or auto manufacturers find optimal point, would that be sufficient to alleviate all of the emissions? Some studies says region braking is really effective reducing emissions, overcoming the heavier vehicle weight. Other studies says no, friction brakes just engages and there's huge brake emissions. This is something to watch, and it's very relevant. Yes.
Yes, I agree. It's really relevant. And our next question is, can you separate newly generated and resuspended road dust? I don't think so, but what's your opinion on this?
Yeah, so this is a great question because we measured at the near road, but we don't know how much of the particles are coming freshly emitted from the brake pad and water surface and then dispersed by air and then dilution and then transported to the measurement location or the community versus how much of the particles were already deposited on the surface and resuspended by vehicle-induced turbulence and then transported. This is a very important question, which is very difficult to answer. So again, I want to give some ideas to the future researchers so that questions can be answered. It doesn't have to be answered by our team. So our idea actually we failed to get funding, but hopefully someone who has funding can carry on this research. And I believe someone in Europe already has done some of this simulation. So the idea was, since our team member Max Zhang has capability of CFD analysis, we want to simulate, because it's very difficult to differentiate what is aged deposited on the surface versus what is fresh in terms of chemical composition and size distribution. It's almost impossible. And so our idea is, why don't we simulate it and see how much we'll be losing in the process, and then compare that with what lab measured emission factors. So the idea is, if you can simulate emissions at the exit plane and then take into account of airflow and deposit, then that should be what is going to be dispersed in the air. And that actually has been done in some well-designed lab studies, especially the one that was earlier than our study that was done by Link Engineering and ERG. And they actually have done quite a lot of analysis of the particle loss in their sampling system. But the same thing can be done in the real world application. And I believe the upcoming project from different agencies, which will confirm the on-road real world emissions from real individual vehicles, will actually help give some data points which computer simulators or numerical people can use it. So my answer is yes. The answer is numerical analysis or some modeling as opposed to experiment.
So the follow-up question from Ping Ding is: have you tried to link road dust with traffic volume, weather condition, etc.?
Actually, we in our final report we actually calculated crosswind speed. So wind is really complicated. So we have a crosswind, we have a wind, and then we have a vehicle-induced wind, right? So as vehicle moves at 30 miles per hour, 60 miles per hour, it generates turbulence in 3 dimensions. So it spills over whatever is in that on the road to the sideways. So both things should be taken into account. What was the question? I'm sorry, I lost my track.
Have you tried to link road dust with traffic volume or weather conditions?
Yeah. So in our report, we actually looked at, we actually tried to find correlation between crosswind speed versus PM mass, and also different part of the PM composition, such as dust. Road dust actually is following very well with the crosswind speed. And going forward, we want to add the influence of vehicle-induced turbulence, but we haven't done that part yet.
Thanks for the answer. And again, the presentation and the final report will be available on this website I'm showing on the share screen. So our next question is from Robert. Since phenolic resin is mostly used in brake pads, did you see any increase in them related compounds in this study?
I'm sorry, I didn't capture your first part.
I'll answer this.
Yeah.
Thank you, Bob, for asking this. No, the answer is no. Our chemical analysis does not include phenolic resin.
Mm-hmm. I will ask Eric Barnes to unmute yourself to ask your question, please.
Hi, thank you. I'm Eric Barnes with the Motorcycle Industry Council. There's been a lot of questions about sources of emissions. Mine is also, but chrome rubber and zinc and other chemicals have been used in road construction, as well as in roadside infrastructure. Have you consulted with Caltrans to identify what materials are in that road, in the roadway where you did your studies? if possible. I don't know that Caltrans would know the details to the extent that you're probably looking, but have you consulted with them on what materials you might expect from the infrastructure and the roadway? And one of the reasons I ask that is I don't know the rate at which the roadway degrades, but would it be possible to differentiate crumb rubber in the roadway from rubber coming from the tires?
Right. Thank you. Thank you for your question. We certainly had a discussion, but at the time, as you pointed out, we concluded that this is going to be drained water issue, not necessarily resuspended dust issue, but we can probably revisit this and get connected again with, Caltrans and just to double check.
Our next question is from Jamie. From your study, can you tell how much near-road PM 2.5 and PM 10 concentrations were increased compared to the concentration measured at the same time frame in nearby FRM sites?
I'll answer this. So there are as Heejang in his presentation pointed out, there's a Pampas Lane FIM site by South Coast, and also for Long Beach, there's also a they call urban background site. The temporal pattern of the near load PM, both PM 2.5 and PM 10, are quite close to those they call urban background sites. The difference probably, I don't have the exact number. For PM 2.5, it will be less than 5 microgram per cubic meter.
Okay, thank you, Xiaoliang. Our next question is from Frank. Did you measure any tire dust in case of no traffic? Maybe it is possible to extrapolate from low traffic to background noise.
Yeah, unfortunately, we couldn't, that's going to be midnight and we couldn't do that measurement because of safety, and also we didn't have enough resources to do overnight measurements.
Right. Our last question is from Michael. Regeneration versus freaking braking varies greatly with programming and drive systems of individual car models and drivers. He'd see it being hard to differentiate them over a vehicle fleet. Can a OEM quantify it over the emission driving cycles they're already using to state a range of brake wear? Do you want to start with the first question? Can an OEM quantify it over the emission driving cycles they're already using to state a range of brake wear?
So the way that this brake emission measurement method has been being standardized is that there's a committee under UNECE in European body, and then they have something called PMP group, Particle Measurement Program group, and they have a working group working with industry and agencies such as CARB. So they are collaborating, and the experts agreed that the test method should be based on a brake dynamometer, so that the measurement uncertainties can be reduced compared to vehicle testing, such as chassis dynamometer testing to measure brake testing. And then in terms of dynamic testing, they also run brake dynamometer in dynamic cycle based on real-world driving brake activities. So the working group already came up with standard dynamic testing method. Then the way they, especially if you look at the previous final report by Link Engineering, you can see that they came up with something called a speed correction factor of emissions, because their testing was based on constant deceleration of certain deceleration rate, right? hard braking, medium braking, or gentle braking, something like that. And then they have a speed correction factor to correct for to give the range of emission factor at different deceleration events. So long story short, I guess what's going to happen is that brake emissions will be quantified based on those brake dynamometer testing, which is going to be a combination of constant deceleration and dynamic testing, from which each brake assembly can be assessed in terms of their emission factors at the same driving braking activities, which is going to be representative of our daily braking events. And so the answer is going to be yes. But then there's no regulation yet. Probably it's coming up. That's not, what researchers know. That's what an agency will say.
Right. Just to supplement to what Henry just mentioned, Robert just said that yes, it is based on WLTP driving cycle, and also Link has developed a California braking testing driving cycle based on this European testing cycle as well. So the question with regards to final report and the presentation slides and also this recording, so everything will be available on this website showing on the share screen probably by the 3rd or the 4th week of June. So you have to process the file and also process the recording onto YouTube. So meantime, if you have any questions, feel free to email me at this email, qi.yao@arb.ca.gov. And I think that's the last question we have on the chat box, and I don't see any raised hand. So if we don't have any additional questions, I think that'll be the end of this seminar. All right, I don't see any questions coming in. All right, thank you so much, Andrew, Xiaoliang, Anthony, and Max for your presentation. And again, the presentation will be available on this website. Thank you, everyone.
Thank you.
Thank you, everyone.
Thank you.
Chi.
Great, thanks.
Thank you.